Alrighty, let's see if this recording will work for us. This is our second attempt at recording here for the first part of the CSC 345 data structures. So welcome everybody. I'm Claiborne. I've been a member of the department either full-time or part-time here for 37 years. Actually came out to LSUS originally in 1974, took a real estate short course, then came as a freshman in 1976, got a degree in business in 1980, met Dr. McKinney, Ms. Hall, and actually had a couple of programming classes from them in Fortran, COBOL, systems analysis. Said, I think that way. So I went over to Tech for a year and a half and was in a pre-master's program, came back and joined the computer science that just started really as a department. We were a subset of the math department. So I got one of the first computer science degrees in 1983 and then an MBA in 1985, and I've been full-time, part-time ever since. And in fact, my classroom there that I normally teach in what's that, 110, I think it is. 210 is where I had my first business computers class. But we're going to look here at data structures and all. And I still have my first data structures book from way back in 1982, and the content hasn't changed, only the way we implement them a little bit. So we'll get that in a few minutes. But you see out here on Moodle, you see you've got the syllabus. And folks, I'm very informal. If we were in class, in person, I'm Claiborne. And you've got my cell phone number, 453-2037. You've got my LSUS email, C#. You got my personal email, csharp@shreve.net. And, I appreciate Dr. Watson working with me on taking over this class, kind of a scheduling issue. But as I've said, I certainly want to set up a time, either Monday evenings or Thursday evenings, for office hours, either video wise or office on campus when they allow us back on campus. So y'all let me know what would be good for y'all, because online is fine, but I like being with my students. So there'll be some homework. You've got a copy of the syllabus, things like that, and we'll kind of be working our way through. But what I'm going to do, as I said, is I'm going to spend the week working on the lecture itself, material from the book, and then over the weekend write the lecture. You've seen here for this one, you've got the Word document, about 20 pages here for this section 1.1 through 1.4, and then also make a video just kind of highlighting some things on it. And this way you've got that to go by, and we're going to try and make this as close to an in-person class as we can. So you see that really we cover the first 5 chapters of the book, and then the back half of the book is for the 346 class. So I know how expensive books are, but at least with this one, you get 2 courses out of it. And so that's good. And as I say, the idea of data structures, a lot of the topics really, I say, are the same. It's just how we implement them. And so we'll do some coding. I'll be learning Java. Y'all might have to help me a little bit. But because when I learned, it was all by rote. I say my first experience on linked list was 800 lines of code for just one of the projects in that course in a quarter. So, but then we moved to Pascal and otherwise now C and then Java. So we're going to learn a lot about, because a lot of the basics here of data structures really will tie to everything later on, and we'll tie some things together. But what I would recommend you do is take the lecture, listen to me talk kind of our way through the Word document of it. And then, as I say, that's how I would study. When we get actually to test, test will be short answer discussion type of deals. Uh, I've never believed in Scantrons. I believe in partial credit for students to have. But we'll work out some things there. Of course, we've got at the end of the chapters, we've got some assignments, and we'll probably assign a few of those. As I say, we'll do a little bit with program examples and assignments. And when we get to the point of you doing the assignments, you can always, if you're on campus when they let us back in, remember the chancellor on Thursdays makes those decisions. My office is right there, 247, TC 247, right across from the elevator, right there on the second floor. And I'm there every morning when we get there before my two 115 classes. So, you're certainly welcome to stop by or get through a class at 10 on Monday, Wednesday, Friday, or, 10:45. Normally I head on out to my other jobs. But, certainly if you want to let me know you're going to come by around 10:45, let me know. I'll wait on you. But as I say, that's kind of where we are. But you'll send assignments to me at csharp@shreve.net. It's just attachments or whatever. Don't send them through Moodle or the SharePoint or whatever type of deal. So as we really get into the first part of the chapter, it gets into some things. But if you look going back at your different levels of languages, you really have 5 levels of languages: machine, assembler, high level, very high level, and natural. And, back originally with machine language or assembler, those were the codes in normally hexadecimal or binary for the computer to work with. Very tedious, but you had full control. You had then your high level languages, starting with Fortran in 1954, COBOL 1959. As I say, my first structured language was PL1 that came out in the late 70s, early 80s. And that's what we did data structures on. Then, of course, in the late 80s, we had a language, or mid 80s, I should say, came out called Pascal, named, of course, in honor of the French mathematician Blaise Pascal. And I found my data structures book from then when we used Pascal. As I say, now it's in Java. So the ideas haven't changed. It's really just how we work with them. Now you have C and Java, which are very high level, almost natural languages, but all of this we're working with data and how it's organized. And so remember, the lowest level of data is a bit, a binary digit. Whether a given location has a voltage or doesn't have a voltage, or whether out on the disk a location has a reflects light, if it's a CD, DVD, or if it's magnetized or not, those types of deals. So, just be aware of a bit. And then bits, of course, are combined into groups of 8 called bytes. And, of course, you're certainly familiar with the various ways of a kilobyte, actually 1,024, a megabyte, a million, a gigabyte, a billion, terabyte, a trillion. But it's kind of interesting that the book actually, over in section, I think it is 1.5, talks about the idea of a word. Yeah, 1.5. And so even though we aren't going to get to 1.5 in this one, but we'll get to that next week. But it talks about words, and you used to hear about the term word primarily for IBM mainframes. And words were either 4 bytes, which was a word, you had double words, which were 8 bytes, or you had half words, which were 2 bytes. So, as I say, went back to a lot of the IBM things. You also had back in the day, you had different forms of handling exceptions. And so, we'll talk about exceptions, but so much of this goes back to original programming. But when you look at how Java handles data, there are really 8 or 9 types, which you're familiar with. But, you have a byte, a signed number between a negative 128 and a positive 127. So you have a declaration of a byte. You have a short integer, which is 16 bits, and it goes from a negative 32, 768 to a positive 32, 767. Or you have regular integers that are 32 bits, 4 bytes, remember, 8 bits is a byte. And that one goes from a negative 2,147,483,648 to a positive. Now, folks, don't worry about memorizing those numeric values. I'm not going to ask you on the first test what they were. As long as you know, okay, we have bytes, we have short integers, we have regular integers, you have long integers that are 8 bytes. And so those actually take up I think I got a typo here. Really should be 64 bits type of deal. And so they actually go from 9 quintillion negative to a positive 9 quintillion. So, but remember, integers are numbers without decimals. And then you have reals, which are your floating point. And those actually, the idea of the floating point goes back to the Institute of Electrical and Electronic Engineers, and you've maybe read about that in a textbook. 754 is just the standard for defining a floating point number, and it's 32 bits, and it goes from a negative e to the 38 to a positive e to the 38. So, big numbers there, but floating points, you've got to remember on a lot of real numbers on decimals that floating point can't store some numbers exactly. That can cause some rounding problems. And so we'll talk about that in a minute. There's actually a class called Big Decimal here in Java that will help take care of those rounding problems. One language, high-level language, which you don't see much anymore, COBOL actually had a round function in it. But of course, Java uses an Intel 80-bit extended precision floating point where available, and depending on the system you're on, you might, for some very small decimals, get different values. Then you have, in addition to, regular floating point, float, you have double, which is a double precision floating point. It takes 8 bytes. And so you have, with it, it's scientific to the 308th power, 16 significant digits. And remember, if you really get into number storage and all that, remember you have the mantissa, and then you have the exponent, and the mantissa is your significant digits and sign, and then the exponent indicates positive or negative radix to multiply the mantissa by. Then our next set of types of data, remember, is character. And remember, every character has a unique bit pattern representation, whether it was a capital letter, whether it's lowercase, whether it's special symbols. Remember, even the digits, 1 through 0, can be stored as a character value, like for an address. So you can have, they're up to 65,535 different characters. If you're familiar with Character Map out under Windows Accessories, then, you can look under it and you will see the unique bit pattern for each of those characters, all the way from Arial to Wingdings. But when you look at characters, as I say, you have several different ways of doing it. You used to hear about ASCII, American Standard Code for Information Interchange. It was mainly used on small computers, microcomputers. You had EBCDIC, EBCDIC, which stands for Extended Binary Decimal Interchange Code, and it was mainly used on IBM mainframes. And certainly don't worry about memorizing what ASCII or EBCDIC stands for. But now your book talks about something known as Unicode. And Unicode has really been a way of expanding all of those character representations because of all of the special characters. So if you, as I say, go out to character map under Windows accessories, you can look for the different fonts and you can see the Unicode representation for every character, special, whatever in there. And then, of course, remember, characters can be combined into strings, and you're familiar with those, and we'll talk more about those as we get into things. And then remember, our last form of data type in Java is Boolean, where it's either a true or a false, a 0 or a 1, and it has 8 bits. So that's just a little bit of a review right there of the different characters. Now, as I said, I'm not going to have you do, a great deal of coding by rote. Luckily, the textbook has got a ability for you to go out and download a lot of the data files or otherwise, and it talks about that website on the bottom of pages 21 and 22. And so it's got a lot of the codes available. I've also, hopefully we'll hear back in the next day or so from the book rep on other material that'll be available to us. And but if you look there at the bottom of page 21, you'll see where it has a link, and you've got this here on like page 6 or so of my lecture printout of go.jblearning.com, and then a backslash, and it's OODS for eCatalog. And then you see a set of numbers 978-144-961 3549. But as I say, that's all there on the bottom of page 21, and it says include these downloaded files, put them all in the appropriate subdirectory on your computer, and then it uses that class path command to maintain the current subdirectory structure and put it in the packages. And as I say, include class path in your new book files directory. So that's going to save us a lot of coding and all that, and we can worry more with some of the theory and otherwise. So as we get here into chapter 1.1, it begins with a little bit of a discussion of where object-oriented programming came from, top-down type of deal, and kind of where all of this works. And you really look at programming, and as I say, since I started off with every line was independent and all that, and you used to in the early languages, your third generation, even your early machine and assembler, you had a lot of go-to statements, and it wasn't easy. And way back in 1968, a computer scientist by the name of Edsger Dertzka came up with a letter to the main journal of computer science back there, Communications of the ACM. And he talked about how we need to get away from go-to statements, go to more top-down programming and all. And he started, as I say, there in the late 60s, trying to get programming to be much more relevant and otherwise. So then you add the first object-oriented programming language, Simula, by Nygaard and Dahl. And so you start seeing better ways of doing it. And remember, object-oriented conveys both information, the attributes, and the behavior, the responsibilities. And it can remember internal information from one use to another. Well, these two gentlemen actually received in 2001, the ACM Turing Award. And that is, kind of the equivalent of the top award in computer science. And we used to have an ACM, Association of Computing Machinery chapter. You see a poster or two about it, was active. But as I say, they received that award for breakthrough programming and object oriented. But we'll talk about how you move data from one point to another. Are you moving the data itself? Are you passing parameters? Are you sending the actual data? Are you passing a pointer? So all of those things depends upon the particular language implementation. But you have objects that are self-contained, easy to implement. As I say, with an object, you can modify it, you can test it for correctness, and so then when it actually runs by entities used by application. And so the book talks a little bit about instantiation of a class, and remember, a class defines a structure of objects. So it defines the structure of an object or a set of objects, which includes variables and methods that determine the behavior. And so it talks about on page 3 using a class, a date example, and the class is several special classes. A constructor is used to create new instances of the class. An observer, they observe and return information based on variable values. And they also talk about even assessors and getters. And then a transformer that changes things in some way. And then you jump over to table 1.1 there on page 5, and they talk about how the different classes, how they can be allowed to work external. So you got like public, protected, package, and private. And just access is allowed. So, of course, if it's public, anybody, it can be accessed anywhere, protected with only the subclass and above, and then package within that package and class, and then finally, if it's private, only within that particular class. So we'll talk a little bit about that. But you want to keep your data in a class as private or protected so it can't be changed. Final constant value cannot be changed by the application. But as I say, if you want to use inheritance, you might want to have that declared as protected rather than private. And so then it gets into a little bit of this thing known as the unified method. And really, that was a way now of defining how your program is organized. And, some of y'all, and maybe some of your early classes, maybe you mentioned flowcharting or pseudocode. Well, the unified method, as I say, is a way of defining things. So it uses case driven. You have a sequence of objects or actions by the user to accomplish some task. And that user could not just necessarily mean a human, it could be another system calling forth to use that sequence of actions. So you have that, it's architecture centric, excuse me. So it's the way the components interact, and it's incremental and iterative, where it's got a series of development cycles, each one building on the foundation established by its predecessor. So as I say, it's become a standard for defining, visualizing, constructing, documenting components of a software system, used to model classes and interrelationships. And as I say, it's got some examples there on page 8. And so much of that is true because you look at the complexity of a program, and there are even mathematical ways of proving that a program works or a program doesn't work. So, that's where this unified method is looking at, okay, how do we make sure that everything is covered? So you get into pages 8 and 9, you have objects, and it mentions that objects are created from classes at runtime. Multiple objects can be created from the same class definitions, and variables actually hold references to objects, but it talks a little bit about applications of objects, object-oriented programming, where you have a set of objects sending one another messages to solve a problem. And then we talk a little bit about Java virtual machines, the application, and all of those things. And you got to identify the classes to solve a problem. But like over on page 11, it talks about a class or a package called util that has a scanner for input of data, and it's looking at valid dates. And the program is where it gets asked for two dates. They come in from the user, it checks to make sure they're valid, and then prints out the number of days between them. Now, the way it does that is you've got back on pages 6 and 7, it talks about this Lillian number system. And basically, that's a built in function to look at whether a number is or where it is. And it goes back to the 1500s when that there was actually a correction of the calendar by the people who were the Pope and the other scientists and all that, 1583, excuse me. And because they discovered that the calendar was off by 10 days, so they added or subtracted 10 days. So they're basically just using that Lillian function to handle whether that a set of code is, or set of dates are valid or not, and the difference between them. And it uses the relational operator there towards the bottom. If D1 get year parentheses less than or equal date menu, and you got the two vertical lines, remember, which means or. And you've always got to remember that different languages have different ways of handling your relational operators, ands, ors, nots, exclusive or, depending on how it's implemented. So always keep in mind your relational operators when doing comparison, things like that. So we'll talk more about those when we get into it. And then section 1.2 talks about organizing classes and inheritance. And inheritance allows you to create a new class as a specification of an existing class. So it's a subclass of an existing class. And if you've got a subclass under an existing class, then that existing class is called a superclass. And you don't have to worry about things. You might might not promote if in the section of code you're working on. The thing you with on inheritance is it might not promote reusability and need complex tracking, but the book talks about something called immutable to protect from future changes. And so you've got to allow that with the idea of inheritance. So you take everything from above and then you can come down and modify it in a class below the original superclass one to make it easier. And so it can extend. They've got an example there of incrementing a date type of deal. They talk a little bit about inheritance trees that can access features only from the class above it. And so, Java works its way up searching to find the superclass to get what it needs. And so they talk like the toString operation method. And it says, since all classes trace back to object, then the compiler will trace all the way back up. And so also it mentions a little bit here in this section about polymorphism. And remember, polymorphism comes from the Greek for many forms, and it allows an object variable to reference different classes at different times during execution, where it's a polymorphic variable or a reference. So you've got runtime or dynamic banding and polymorphism go hand in hand. And so there'll be some examples later on about how to create versatile and adaptive classes. And then kind of the last part of this group, as we're getting into it, is packages. And as I say, packages let you group related classes, organize files, where things can be compiled separately. You have common class files. You can avoid naming conflicts. Two classes can have the same name if in different packages. And so if you're doing packages, as it shows there, you have to say package and then the name of the package, semicolon. And then you can import needed declarations into it. And you have different compilation units. And it says you can only have one public class per file, but the package name and public class name are used in compilation. And if you have the same package name, then public classes under those can be imported by an application. Or it talks about how you can have file names.java match exactly to be in the same directory as the package name. So as you import in the package name, and we'll spend, I'm sure, a lot of time on this, it says, like import package name dot asterisk semicolon, or import package name dot class name. Remember that asterisk there on top of 21, import package name dot asterisk. Remember the asterisk goes back to old original Unix or DOS, where the asterisk in a file name said any name is usable. And remember, if you look at like the files command or otherwise in Word, Excel, and you see asterisk dot asterisk, for all files, it's going back and looking at way back from 1981 when DOS was set up. And of course, Windows is a successor of it, type of deal. So let's say the compiler will search downward for subdirectories and files and will import as need be. So we get over to section 1.3 and it talks about exceptions. And exceptions are so important to handle. Either you as the programmer or the system handles them, whatever type of deal. And as I say, you can get the wrong type of data maybe entered. Maybe you're trying to read a file and you encounter an end of file, or a control key combination, or invoke a null, or passing an out of bounds value. But languages have to be able to do data validation. As I say, back to the old third generation languages. Fortran, COBOL. In Fortran you had end equals when you were reading a file. Or COBOL add-in. Our old IBM 370 machine or assembly language, you used to have OC7 or OC4 data or operation exceptions. So as we've moved up from those lower level up to the higher level languages, your fourth and fifth generation, then you can much easier define the exception, a subclass of Java's exception class. You can generate or raise an exception using the throw statement to announce that an exception has happened. And then you can handle the exception. And there's a statement called try catch to discover that an exception has been thrown and take appropriate action, because you want to try within the program, either as the programmer or hide it in the class type of deal, where you don't have a program abnormal ending, or remember the old Windows blue screen of death if a program died on you. So you can recover from an exception, and then where it not be fatal, you handle it, either force the programmer to handle it, or you can hide it in the class where the programmer doesn't have to handle it. But in all cases, you've got to look at things. So it looks here on 23 through 27 with an example of reading a date and taking that date and just a little subset of it on the bottom of 24, where they're just looking at the month and saying, hold it, well, let's look at the month. Is the month less than or equal 0, or two vertical, they'll say very bottom there, page 24, or new month greater than 12. And so if that is true, then it throws the exception, an out of bounds exception, saying month, new month, then illegal. Otherwise, it makes month equal to new month. and day equals the new day, and then it's going through looking for the year and all those types of deals. So there's always a lot of data validation that we have to do. You know, the old idea of making programs idiot proof. So, you know, if the user enters a value that's way out of bounds or otherwise, then, you know, it can be handled. And so those are always important. But finally, you go through and you finally get over to section 1.4, data structures. And so, as I say, you look at the types of data structures, whether it's arrays, linked lists, stacks, queues, sorted lists. We'll talk about all those in a minute. But those basic structures, as I say, you pull out, if I were to be lecturing instead out of my original book that I took data structures in, you'll find the same data structures there. Just how they're implemented and all that has maybe changed. But you're looking at complex interrelationships between the data. We'll look at a language's primitive data types, all of those things. And I say you've got to look at the organization of them to represent the data. But you build with these basic structures everything from it. And I don't care whether we're talking about working with data or we're talking about organizing files or whatever. But the first data structure it talks about are arrays. And you see arrays in any language. I mean, even you go down to one of the very simplest programs that we used to talk about or languages, BASIC, Beginner's All-Purpose Symbolic Instruction Code. Well, you had a very simple array set up in BASIC, and you had it in all of the others. But remember, an array is just where you allocate some block of data, you know, and then you say, well, how many occurrences of each of these types of data are there? So if you had integers, well, you would have 10 copies or 10 spaces for that integer value that you could put things in. So if you knew each integer, let's say, was 4 bytes, well, if you wanted to get to the 7th position, you'd just be at the 28th byte of that group type of deal. So, you know, memory locations by name and number, that's used in most all of them. You have multi-dimensional arrays where you have such a row and a column. You're familiar with those. Now, one thing that you got to worry if you get into some nitty-gritty on some of the languages, some languages do it row and then column within each row, or some of them are column and then row type of deal. So sometimes if you're really getting into a language, you have to look and see, you know, how it handles it, how it's implemented. But certainly arrays are a very simple form of data structure and are really common across most every language I've ever worked with. And then the next one they talk about is linked list. And a linked list is, as I say, where each separate element has a pointer to the next item. And Java has a link mechanism built in to study and use linked list, and so we'll certainly do that. Certainly, as I say, much better than trying to implement it by rote. As I say, my first experience with linked list was 800 lines or so of PL1 to implement it because PL1 didn't really have a good way of handling it. So as I say, we're going to let Java handle a lot of the nitty gritty. We'll deal with the code or the implementation of it and hopefully make it easy. But you know, when you look at, you have the element and a pointer to the next item, and a pointer to the next item, and a pointer to the next item, all the way to the very end till you get to a null pointer. And of course, you have a pointer at the very top to go to the first element of the linked list. But you can add things in the middle of it, you can delete, all by changing pointers. And whether it's a linked list for data, but also one of the implementations you have of linked list is how files are stored out on your hard drive. Is, you know, you maybe have heard talk about tracks and sectors, where you have those tracks, those concentric circles, and then each track is divided, or each part of the disk is divided into a pie-shaped portion called a sector. And it used to be we had either hard sectors or soft sectors on a hard drive, but we don't worry about that anymore, thank goodness. But as you move from sector to sector, there's a pointer on the file allocation table to tell you when you reach the end of this sector how to go to the next one, to the next one, and so on and so forth, till you get to the last track and sector of the file type of deal. So I say pointers are used everywhere, and we'll deal with those. Now, the thing about both linked list and arrays is they're implementation dependent. The idea of how you work with them, how you define them, how you access, like the subscripts in an array, is very much dependent upon the language you're using. Whereas you have also implementation independent data structures, and those are not tied to a particular language or approach or whatever. So you really have kind of a two set of these implementation independent. You have stacks or queues that depend on when the data is placed out onto the structure. Or you have other forms, sorted lists, maps, trees, and graphs, that the value of the element is what we work with, or the position. So, as I say, you look at a stack, and we'll look at various operations. Push puts an item on it, pop takes an item off of it, top points you to the top of it, things like that, and we'll get into those. But, the best way to think about a stack is you go to the restaurant and there's that round thing of all the dishes, and you can take a dish off the top, and then the spring at the bottom pushes the next dish up. Likewise, if they add 10 dishes to that stack of clean dishes, then it pushes everything down. So you have stacks as a way of in and out type of deal. You can only get to an item that's on top, and the computer keeps track of pointing, and you do to everything else, but you can't get to it. Or a queue is what we're very familiar with. Remember, queues, first in, first out. So the queue, you're just constantly working your way from front to end, and as you add something at the end, it pushes something forward. And we've all, especially over the past few years with waiting lines and maintaining 6 feet of distance and all that, we're all very used to queues. So stacks, remember, are what's known as LIFO, last in, first out, whereas a queue is FIFO, first in, first out. And you certainly even hear those terms, even if you ever go over and take an accounting, as for different ways of doing accounting, inventory, and we're not going there. But the other forms that you see are sorted list, maps, trees, and graphs. And so sorted list, as I say, are an implementation really type of deal. It's independent. And sorted list, you could use arrays, linked list, all of those things. Remember, with a sorted list, every element has a predecessor except for the first one, and every item but the last one has a successor. And a lot of the part of this book, chapter 7, chapter 11, there you'll get to in 346, deal with different sorting. And so you'll certainly spend a lot of time looking at different sort algorithms, binary, tree, whatever types of sorts, how more efficient for different types of data, insertion sort. So you'll certainly learn a lot more about sorted lists. We'll look at them some. Then another form here it talks about are maps, where each element has one or more keys, and all those keys are unique. So, you look at yourself, your data out on My LSUS or Compass. Well, what's the key? your student number, right? I mean, you can't do anything at LSUS without a student number. And you know, LSUS was one of the first schools to go to randomized semi-student numbers. Back when I was on your side of the desk, it was our social security number. I mean, faculty, you know, you'd do a test on Scantron or whatever, and they'd put a note on the front of their door with your social security number, your grade. Yeah, that'd go over real well with the data privacy people these days. But, you know, you can have the key of your student number pointing to all the information, whether it's your personal information, your contacts, your classes, whatever. So you can have a key field that goes to that. You might be able to reach it through maybe one or two. There might be a couple of other keys going to it, but those keys each will only point to a particular info record. And so you have maps, where each element has one or more keys, but all the keys are unique, and a key maps to a single location type of deal. Or you have trees, and now remember, trees and graphs are nonlinear as such. A tree, each element has a single parent, and then as you work your way down, your children of the tree can then have children of themselves, things like that. But each node, each element can only have a parent, and of course, a parent can have many, many children. Now, the very top of a tree is called root. And so, you know, you look at your basic file structure, you know, out under Unix, DOS, Windows, whatever. What do we see? C:\\/ root, right? Or C:\/ if it's Unix. And so, you know, that is the basic structure. And then you have off all of those root, you have the various subdirectories, things like that, and DOS and Windows and all. So if you'll think about a tree structured directory like your files, and you also have, as I say, in Java with trees, you have the inheritance mechanism going in there. And then the last data structure we'll talk about are graphs, and graphs have multiple links between the various points called edges that describe the relationship among the various vertices. Sometimes those vertice values can either be distances or whatever. But as I say, the difference between implementation, dependent, and independent categories, as I say, originally it was how they were implemented. Now we look at more abstract and implementation levels. And as I say, all of these things, all of these data structures are there to have for us to use in managing the data. And so as we're talking about them here in the class, you know, you'll think, okay, well, this is a perfect example for an array, or this is a linked list, or this might be a tree or graph. So that's where we're going to try and do on this is give you a lot of tools to think about, just as learning multiple languages. You say, okay, well, this is the strength of this language to do this with. And as I say, my forte is your older languages, COBOL, Common Business Oriented Language, Fortran, Formula Translator. Fortran really was not good to do a paycheck, but I wouldn't want to do scientific calculating in COBOL. But the same thing ties here too, learning about these different data structures and how they can be used, how we can work with them, things like that. So when you get to a given problem in an upper level class, or hopefully in a few years when you graduate and are out there making lots of money and come back and endow a scholarship here at LSUS, which we've had happen. You know, it's amazing where some of our graduates have gone to. Some of y'all are maybe familiar with the video game, I think it's Doom. Was actually some of the programmers way back in the late 80s, 90s on Doom were our graduates. And so, they've made so much money that they've retired. One of them I know of lives up on the lake up in North Arkansas and, just counts his royalties and fishes. So anyway, we're going to look at these data structures. We'll work together. As I say, y'all let me know how we're going to be able to do some combination things. And hopefully this recording here, the lecture worked. I'm going to double check it. And I'm going to not only post it out to YouTube, but also I'm going to probably send y'all an individual email on it and see if that doesn't work. And as I say, this weekend I'll do the next set of lectures here for the back part of this chapter on sections 1.5 on, I closed my book too quick, on basic structuring mechanism. As I say, it talks a little bit about memory and references and gets into arrays. And then it talks about algorithms a little bit on order of growth and complexity. So we'll get into a little bit of that, selection sort, all those things. So expect another lecture over the weekend. And y'all call me, email me, whatever way works easiest for y'all to reach me. And folks, remember, I'm Claiborne. And so my cell is 453-2037. And you got my email. So any way I can help you, you let me know. And I look forward to us having a great semester. And I think I will stop recording and make sure this worked.